right, homework handouts out. If you would please go and hold them up so that I can see that they are completed. And good, good. All right, the key to solving these problems, of course, is getting a good free body diagram. So on the very first problem, we've got a man rolling a cart loaded with books up a ramp. So that's the ramp. That's the cart loaded with books. You say I can't see the wheels. That's okay. All right, by the way, since there are wheels, we can assume there's going to be less friction, right? So we'd expect lower friction. Now, I will say for rolling, that's kind of a high coefficient of friction, 0.215. There may be sticky wheels, right? Like a shopping cart that it gets, yeah, you know what I'm talking about, okay? So coefficient of kinetic friction. All right, it's a 42 kilogram cart of books, which actually isn't that bad for a cart of books. The ramp, it says, is angled 18 degrees above the horizontal, so you have an 18-degree angle here. Let's see, what are some of the different forces in play here? Audrey? Weight. And although weight technically acts straight down, we're going to treat the weight as though it acts in two different ways. Into the ramp like this, and then down the ramp like this, but we'll translate that vector here. So we're going to call into the ramp class the weight in the y, and we'll call the weight down the ramp the weight in the x, because we're going to look at the y and the x like this. We're going to look at this surface as the x-axis. This angle right here, class, is an 18-degree angle to match right here. And okay, what's another force that we have acting on this object here, on this cart loaded with books? Kendall?
The normal force.
Okay, the normal force pushes right back up out of the ramp, countering the weight in the y. Michael?
The man.
We have the applied force going up the ramp, presumably pushing it up the ramp. I suppose it's possible, could be pulling it. I'm going to have the applied force up the ramp, doesn't matter which side of the box I draw it on. And then the final force, class, is friction, which in a perfect world with wheels should be negligible, but it evidently isn't. The first force we should always find, class, is the weight, unless of course it's given to you. Here it was not. And so we find the weight to be what, Audrey?
14.6.
All right. But as soon as we get the weight, that isn't in the x or the y, so I want to then use that number, break it into the two components. I like to find which component first, Kendall?
Y.
Y. Why do I like to find the y first? Because if I find the y, it tells me the
normal force.
and once I know the normal force, I can find the friction force. So let's start with the y. What did you get for the weight in the y?
391.454.
Good. Keep in mind that the right angle is here between the x and the y components. This here, the weight, is the hypotenuse. So I have an 18-degree angle, I have the hypotenuse, and what I'm finding is the adjacent. So we can say that the cosine of the 18-degree angle equals the adjacent weight in the y over the hypotenuse, which is the 411.6. We just multiply, and that's where that number comes. But since that's the weight in the y, Kendall, you said that's also the normal force, 391.45. And obviously those two, if they always cancel each other, you know, for their own sakes, they serve no purpose. They're just going to, you know, form translational equilibrium in the y anyway. The purpose of the normal force class is to find the friction force. And so I'm going to take that normal force times the coefficient of friction, which was 0.215, and I come up with how much friction force now, Kendall?
84.162.
And that's what I'm going to put in the memory. There's no need to put this in the memory because you're going to turn it right around and just copy it again. There's no need to put that in the memory because you're just going to use it to get that. This is the number that needs to go into the memory. All right? So I say it, let me make sure I actually do it. All right, then what do I need to find, Michael?
The weight down the ramp.
The weight that's pulling it down the ramp, right? Countering the man's efforts. And frankly, it would be pulling it down the ramp even if there were no man. Just box. Down it goes. All right, how much weight in the x did you get?
127.19.
Good. With relation to the 18-degree angle, this is the opposite. I know the hypotenuse, so we're going to say that the sine of the 18-degree angle equals the opposite weight in the x over the hypotenuse, 411.6. we do get 127.19, blah, blah, blah. I'm going to go and put this into memory too, so that the two forces that are acting down the ramp, working together down the ramp, are both in the memories. Now, there's a lot of different directions I could go here, and the question asks, if he applies 310 newtons of force, what is the acceleration of the ramp? Other problems I could find. If there had been no man, I could have found the acceleration of it without a person touching it. In which case, friction would not be acting down the ramp class, but rather up the ramp. If all it was a cart loaded of books on a ramp and I step away, friction acts this way, however sticky the wheels are, and weight pulls it this way. And the two would counter each other, weight in the X would win, wouldn't it? I could also say, what if we just want to move the box at a constant speed up the ramp? Well, if it's a constant speed, there is no acceleration, right? So if I wanted a constant speed, what would I do to find applied force class? I just find out how much this is together. It's what, about 211-ish, 212, right? I just add those two numbers together. That's how much he would need, right? Just to match it, just to produce translational equilibrium, a nice, steady, unaccelerated rate. But if he actually wants to accelerate it, he's going to apply more force. In this case, he applied 310 force. He didn't need that much force, did he? He wins, and he wins pretty big. I need to find, class, the net force, the sum of the forces in the X, by taking the 310 minus the weight in the X that resists him, minus the friction force that resists him, and the sum of the forces, or the net force class, the resultant force is 98.6. Hey, no fever. That's good. And then we're going to take the 98 points. I did that on purpose right now. Anyway, the 98.6 newtons of net force class to find acceleration gets divided by the mass, which was the 42 kilograms. And so this box, this crate rather, or cart loaded with books, is going to accelerate up the ramp at a rate of 2.348, blah, 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 or rounded 2.3 meters per second squared. How many had that final answer? All right, questions on this? By the way, what if they told us the acceleration we wanted? What if they said he wants to accelerate it at 1 meter per second squared? Well, then I know that the sum of the forces would need to be 42 to give us a 1 meter per second squared, correct? And so if you had to win by 42, I'd simply add these and tack on an extra 42. So there's a lot of different ways I can approach a ramp problem. This problem, I chose to approach it this way, where I gave you a force, you were finding acceleration. Questions on a ramp problem? Going once on questions. You're going to see some type of ramp problem on the quiz in a few minutes. Any questions? All right, let's go to the next type of problem, which is the boy on the swing. Speaking of which, this weekend, I took my kids to the park. Well, my wife and I did, and so I was pushing kids on swing. And I couldn't help but think, as I was pushing Andy, my youngest, which I was actually pretty impressed. Like, it wasn't even a baby swing. He's not even 2 yet. He was sitting there holding on to the chains really good, pushed on the swing instead of on his rear end, so I didn't push him off this time. See, you learn lessons. When you're the 4th born, you're safer, right? It's the 1st born that's not safe. Maybe even 2nd born isn't safe. By 4th born, we got this figured out. So I'm pushing him on the swing really good. And anyway, I didn't tell him about the physics behind it. All right, this is bigger than my kid, though. This is a, let's say a 3rd grader probably, maybe 4th grader, 3rd or 4th grader. If it's an American, it might be a 2nd grader. Anyway, I digress. If it's an Asian, it's a full-grown man. Just kidding. No hate here, no hate. We're just making jokes, right? We love everybody. Anyway, I just lost all my Indian subscribers. All right. Oh my. Anyway, love everybody. Everybody. God died for everyone, to save everyone. We love everyone. We don't discriminate. Anyway, so on that happy note, Michael, who's definitely not 29 kilograms, read this for us.
A 29 kilogram boy is on a swing and his dad pulls him off.
Pulls him off? Oh no!
Pulls him back at an angle of 24 degrees from the vertical. Find the tension in the chains and the force that the dad has to exert.
At least he didn't say he bumps him off. In the States, that's slang for, well, you know. Anyway, all right. So that's vertical. Swing isn't vertical anymore. Swing is back. Now I did test this, okay? I will admit I'm enough of a nerd to pull my son back and try to hold him there. That's hard to do, okay? It's really hard to pull. It's so much easier to push, okay? So I'm like, who maybe pushes boy and holds boy forward at 24 degrees? Because I was thinking about it like real life. Do you really pull a child back on a swing? Nobody pulls a kid back. They push the kid, right? It's what you do. Anyway, the point is the kid is back at an angle of 24 degrees from the vertical. That's the kid, all right, right there. Let's just say dad pushes the kid back at an angle of 24 degrees because that's more anatomically feasible and doesn't really matter. The point is the kid goes back 24 degrees. And we said principle of transmissibility, dad pushes, dad pulls. It really doesn't make a difference as far as physics is concerned. It just makes it easier for dad, all right? So maybe the kid is even facing this way. Oh, it pushes him forward an angle of 24 degrees. Really doesn't matter. You can't even see the kid's face, all right? Now, these are not the only two forces though. We don't just have, what's in the chains class? Tension. We don't just have the tension in the dad. There's some other things going on here too. What else is going on, class?
Weight.
Weight. Kid has some weight to him. And this tension, because it's an angled force, we can think of tension as behaving in two ways. Tension is acting upward, resisting the boy's weight, and tension is also pulling toward the left, right? If dad is pushing forward, it's pulling back, or if dad is pulling back, it's pulling forward, right? Which is why, you know, you push the kid and then the kid doesn't stay going forward. That would be strange. You give him a push and, you know, anyone ever actually gone all the way around? Like I've seen kids try it where they go all the way around. Nobody's ever done that. Okay.
I was always scared of hitting my head.
It would probably be a bad day all around. Yeah, it's probably not safe. I'm not advocating for that. All right, so anyway, what's the first force we should always find, class? Weight, because it's reliably, consistently there. We just multiply mass times gravity. I don't have it written down. How much does the kid weigh? 284.2 newtons. And if that's how much weight pulls kid down, and kid isn't falling down, then apparently, class,
That's the normal force.
well, not the normal force, but the upward force, the tension in the Y, 284.2 newtons. All right, now, we know that the X and Y components are perpendicular to each other. We also know that if this angle is 24, class, the angle down here is 24. Chains to the vertical above the boy is also still 24 degrees. So if I want to find the tension, well, the tension, class, is the hypotenuse. Tension in the Y is the adjacent. So I'll simply use the cosine of the 24 degree angle to say that's equal to the adjacent 284.2 over the hypotenuse, which is the tension. Here, though, instead of multiplying, class, I'm going to have to divide away the cosine of 24. And how much tension is in those chains that hold up said boy? Class?
300.
Good. And then round it off. Is it 3 sig figs, I hope? Yes, it is. So we get
311 newtons.
311 newtons. Did we get that for the tension? All right, questions on that? All right, the next thing says, find the force the dad has to exert. Well, why would the dad have to exert any force at all? Because the chains aren't just holding up the boy, but as soon as the dad starts to push the boy forward realistically, or in a problem, pull the boy backward, class, the chains are also pulling against him. They're pulling backward if he pushes forward. They're pulling forward if he pulls backward. Chains are resisting him. Whatever the tension in the X is, that's going to match the dad's applied force, unless dad pushes harder than the tension, in which case the kid falls out of the swing and lands on his face and cries. And Mom comes and gives Dad what for, and it's a bad day for everybody. So let's just say that doesn't happen, okay? We want to live in a utopia here. All right, so I really, in order to find applied force, I need to find tension in the x. Well, with respect to the angle class, tension in the x is the opposite. And I know the adjacent, so I should use the tangent of 24 degrees. Say that that's the opposite, tension in the x, over the adjacent 284.2 newtons. We'll cross multiply. And how much tension is there in the x class?
127.
126.53, which means how much force does Dad apply?
127.
126.53, or rounded off, it is
127.
127 newtons. And there's the second answer to the problem. Did we get the second part of it correct? All right, questions on the swing problem. Questions on swing problem. All right, the last type of problem we had was an object that was sort of suspended, if you will, by a cable. And that's what we have here. 12 kilogram sign hangs from the end of a support bar. Cable is attached above and at the end of the support bar, forming a 35-degree angle with the bar. Find the tension in the cable. All right, so now, it doesn't tell us where the support bar attaches, presumably to a wall, okay? I suppose it's possible, but I've seen this as well, right? It's just a post, and you have the bar sticking off the post. For instance, you notice Golden Donut? As you go through the drive-thru, there's a little random metal bar that didn't used to be there with another metal bar with a sign hanging down telling you the clearance, so people wouldn't hit the awning again, because so many times tall trucks went through and clobbered their awning and knocked it up. So anyway, maybe that's all it is. Maybe it's the Golden Donut clearance sign. There's the clearance sign. And it says, don't be stupid, okay? And if you hit the sign, don't go through our drive-thru. Park in the Popeyes parking lot. They don't take up space in our parking lot. Anyway, 12 kilogram sign. But somewhere there's a cable that attaches, so there goes my Golden Donut theory. It's a wall again. All right, wall, support bar, cable. And the cable, it says, attached above and at the end of the bar, forming a 35-degree angle. Now, realistically then, there's the object, there's the bar, there's the cable. Blow it up just a little bit bigger. The cable, of course, class has tension in it. The sign has weight that acts straight downward. And the cable, like the swing chains, has tension both X and Y. Upward in the Y to counter the weight, and then also has a tension inward that causes what to develop in the rod or in the support bar? A compression in there, right? But as we already just noted when we did chapter 5, the compression would be minimal. We can ignore it. All right, it doesn't ask about the cable. It doesn't ask about the bar, rather, the compression force, so I really don't care too much about this. What I care about, first of all, is the weight, as always. How much weight does this sign have? Class? 117.6 newtons, which means if there's 117.6 newtons of weight pulling down, then if the cable is supporting everything, how much tension upward? 117.6 newtons. Again, we don't want the bar to slowly deform over time, so we want the tension in the cable to support everything. Now, couple thoughts. This is the 35-degree angle. So you could say that this is also a 35-degree angle. In which case, when it says find the tension in the cable, which is the tension right here, I'm finding, class, the hypotenuse, and I know the opposite, so I would need to use the sine of the 35-degree angle, and that's going to be equal to the opposite 117.6 newtons over the hypotenuse, which is the tension. The alternative, of course, would be to say, well, if we have a 35-degree angle here, how big is this angle? 55. But evidently we don't want to do that because that requires more math, right? Why would we want to do more math? That's just silly. And if I did, I would be able to use cosine adjacent hypotenuse, but I'm not so married to cosine that I have to go doing more math. I mean, it's not worth it. So I would do it this way, where once again we need to alternate and divide. And how much tension is in that cable, class?
105.
We'll round it off, we'll say 200, 3 sig figs I hope, yes. 205 newtons of tension. What if it had asked for how much compression force was on that rod? I would use the tangent here, the opposite over adjacent, and I could say that the tangent of 35 equals the opposite 117.6 over the adjacent tension in the x, which happens to equal compression, because that's what the compression is that tension in the x. Again, I could alternate and divide and get my answer there. But I didn't ask for that, so 205 newtons is our answer. Questions on that last problem? How many got the 205 newtons of tension? Ooh, none of us. Okay, do we need to work one more like this before we take the quiz? Because you will see a problem like this where something is suspended off the side of the building.
I had the wrong angle.
Had the wrong angle? Okay, so you did try to do the angle, you just got 45 instead of 55?
No, I was confused because I didn't see with the bar, so
So you put the 35 right here already and then used the cosine. Okay, gotcha. All right, any other comments, feedback? That was good feedback.
I multiplied instead of divided.
Okay, did you take the time to write it out?
Mm-hmm.
Okay, yeah. So you're just like, oh, I need to use the sign, you just multiply. Yeah, don't default to multiplication because you don't know, sometimes you multiply, sometimes you divide. If you just write it out every time, you don't have to worry about screwing it up. So that would be my admonition on the quiz.
I'm not quite sure what happened. I think I faulted myself in several ways. I had 226.
You had the weight at 117.6? Did you try to use the 35-degree angle or did you use the 55?
I'm not sure. I used memory values.
Okay, all right. Strategy tip, write the numbers kind of like you see me doing, just write them down as you get them, you know, do put things in memory as you need, but the more you write, just helps you kind of see what you're doing as you go along. That might be a strategy tip there. Do we need more practice or we feel like we're ready for this quiz? I'm getting a nod. That was a bad way to phrase it. How many say, I am good to go, I understand it now, I may not have gotten it, but I'm good? How many say, I would really like some more practice? Everybody watching on YouTube just raised their hand. All right. All right. Well, we did not raise our hands for that, so I suppose if you are watching on YouTube and you say, I am nervous about this, then we'll arrange for a video chat if that's possible. And but let me know if you're feeling a little nervous about the quiz before you take it. We here are going to go and take the quiz. So go and clear your desk except for a clean sheet of paper, a pencil, and a calculator. Clean sheet of paper, pencil, calculator, and everything else away. First and last name at the top of your paper, along with today's date, which is 11/7/22. 11/7/22. And this is quiz 12B. Quiz 12B. All right. Very straightforward quiz. There's 3 problems. Solve them. Show all the work that you need to show. When in doubt, show it, okay? And we'll go from there. We may end the lesson here, so I'm going to go and put the homework on the board. If these students finish quickly, we'll go ahead and get into our new material, but otherwise, I'm going to provide the homework now just in case we take the rest of the hour, and I'm prepared for us to do that. All right, you may begin.